All right, so welcome to another lecture of probability and statistics, lecture number 9. So I think we have in total 13 plus an extra one that will explain how the exams will look like. So we are reaching the end. This will be more pure statistics, and we will touch now we're trying to explain what a hypothesis testing is. As an introduction to this, we'll have the binomial test, which is one statistic test that you could use using the binomial distribution when you have variables that are binomially distributed. And then we'll talk a little bit about what a p-value is and some examples as always. All right, so far we have been looking at mostly descriptive testing, right? So we have some random data that we collected, and we calculate the mean, the average, the mode, the median, and then we measure how much the data spread over the over these variables using standard deviation, the quartile, so on, right? So we have been. If you have a data, you want to characterize it or describe it, and these parameters basically tell you how the data look like. From that, you can have a sense how the distribution looks, right? But you cannot really make too many conclusions about this, right? So what we're going to start looking now, and we already started a little bit last week, is to go to what is inferential statistics, right? And this is where you try to estimate, or if you want, it's kind of an extrapolation of what you have in your hand to what it should be in reality for the whole population. And so we have been using estimation methods to estimate parameters like the mean, the standard deviation, parameters of the gamma distribution. Last week using the methods of moment and the maximum likelihood estimation, right? So these are inferential statistics. Now we're going to move to what is hypothesis testing, and this is very useful, especially when you want to know if something is better than others. Or in research, for example, it's very useful when you have, for example, a new therapy and you want to know how good the therapy is compared to other therapies. Then you have to test statistically, and you use these testing methods. And you will see that there are two basically worlds. One is parametric test, and the others are the non-parametric test. And we're going to go a little bit through this as an introduction. So to motivate, let's say, hypothesis testing, we're going to go to one example that is not deliberately put it here, but it's from the book, or the famous book of Fisher, The Design Experiment, where they say, can you detect if you drink milk with tea, or tea with milk, can you detect what was first, the milk or the tea? So supposedly, some ladies were claiming that this is possible, and they were saying that they are very good at that. So to motivate that, let's say that you have your aunt, and this aunt is very good at discriminating when you have put milk or tea first in your tea with milk cup. And so let's say that we want to test that, right? So we will ask our aunt to drink several cups of tea, and we ask the aunt to tell us what was first. This, as you can see, you can set up a Bernoulli experiment, right, with n trials, so it's kind of a binomial distributed data you will collect. And you want to test if this binomial distribution will have the p equal to 0.5. So that would mean that by chance our aunt is guessing what was first. So if it's larger than 0.5, the p, then we will say, yeah, well, maybe it's not by chance, but she's really good. If it's below than 0.5, then we don't care because it's even less than by chance, so it's even worse, our aunt. So we care about p that are larger than 0.5. So for that, we have to set up, so we want you to test if our probability of our ant guessing the cup of tea is equal to 0, again, if it's equal, if larger than 0.5, right? So we have to create kind of a concept here of setting the hypothesis. So you have a hypothesis that your ant is not that good, or your ant is very good. So then you set up two kind of hypotheses. One that you say that your ant is not that good, that she just by chance does that. And this is what is called the null hypothesis, or sometimes the control area. And the other hypothesis, which is called the alternative hypothesis, is that your ant is actually good at guessing the tea, the milk and the tea, in the tea with milk cup. And that means that the p will be, in this case, larger than 0.5. So this is the first thing that you do when you do hypothesis testing, is you have to set up your hypothesis, right? Then you will have to collect data. So let's say that we ask our ant to drink 20 cups of tea. Well, it's, let's say, a relatively small number of samples, but I guess drinking more than 20 cups of tea will make it complicated to, or at least you will be dizzy, I guess, after drinking 20 cups of tea. So let's say that out of these 20, you say, if my ant guessed 14 of them that correctly, then we say, well, 14 over 20 is 70% of the chance of the times, right? So let's say that it's a good threshold to say, okay, after 14, we say she's good. So now our hypothesis is put it in the way of how many trials she did it well. So if she did it more or equal to 14 times good, then we say we can go for the alternative hypothesis and say, and reject the null hypothesis. If it's less than 13 or equal to 13, we say, no, we stay with the null hypothesis. She is not better than chance, than just flipping a coin and say what happened. Okay, so let's say that we do that. Then we have, right, a Bernoulli experiment repeated n times, so we have a binomial distribution. And we set up something that is called the power function, or the Guten function in Deutsch. And basically, this is what it's going to tell us the probability that our ant is going to be good or not. You can see on the right, I think, you can see on the right here, how this distribution look like for, if you have 20 times, 10 will be our 0.5. So after 14 is our threshold here. Yeah, I think I cannot, unfortunately, but you can see the red dot here, right? So after 14 will be our threshold. So if she is to the right of 14, she will be good. She's not by chance only. So if we calculate for the p of 0.5, and we say that we have our threshold of 14, so you calculate the probability to be from 14 to 20, then what you get is a probability of 0.057. So there is still a chance that you are making a mistake, right, by saying that, that your ant is really good, but she's not that good. But the chances is 5% of getting this error. And this is, you will see how this develops later on, but this is the key of hypothesis testing, is you want to be some kind of sure that what you're saying is true with some kind of error. And 5%, I would say, is acceptable, I would say. And so 5.7%, you're saying that your ant is good with a threshold of 14, which translates to 5% error probability of having an error. And this is this probability that you see here, right? So in the distribution, you will see that. All right, so with that, we can make it more formal, this, and then we can call this 5% that we saw before our alpha level of error. And this is something that you will set up arbitrary, and you will say, I accept anything that is below this alpha error. Okay, so in this case, let's say we say alpha error 0.05, so 5%. If it's below that, we are OK with the error, and we say whatever we say is correct. So this will be our first thing to do. And then you will have to set up. This will, of course, give us the rejection or acceptance of the null hypothesis, right? What we set up with the 14 was this threshold here, right? That here I call it C to make it more general to anything. So let's say that you have any distribution, our 14 will be C. The probability that we calculated here, this probability here of our threshold, is the probability for that particular threshold. Now, this will be your threshold that you say, after 14, I am OK. Now, your AND can be below that threshold or after that threshold. And these are these red P1, P2, P3 that you see here. So they will be located in some. It will be 15, it will be 13, it will be 16. And each of these P here will have associated a probability here. This probability is what is called the p-value. Okay, so it's the true, it's the probability of the realization against the distribution that you have. Okay, so the lower this p-value, the better is your assessment because you are making less error. Now, this is important. So if our p-value is, of course, to the left of our critical value C, you end up in the accepting the null hypothesis. If your p-value is to the right of this C, you end up rejecting the null hypothesis, right? Because it's the 14 to the left, to the right. So this with the binomial case. Now, one thing that is important is that it doesn't mean that you have a p-value is actually true what you are seeing, because you have to always put it in context to your research. This is a very good explanation on, this is a highly correlated with a very low p-value of a correlation between the global temperature and the number of pirates in the world, right? And you can see that it's highly correlated that the lower the number of pirates, the higher the temperature. So I would say that we are all agree that this guy that has nothing to do with global warming, right? But still there is a highly correlated value here. So what I say is that the p-value, it can tell you something, but it doesn't tell the whole story. Then you have to put it in context of what you're doing. So we saw that with a threshold of 14, we will have an error of 0.057, right? This threshold is what you can manipulate. This is one thing that you can do, like it will be your alpha value, right? So one thing will be, well, you can move it to the right, and then you have less chance of making an error, or to the left, whatever. So this is what I'm showing here. If you select a threshold of 15 or 16, you can see that the probability of making the error is getting really low. So this is one way of adapt your, how much you are willing to be wrong, or how much you're willing to, how much probability you're willing to give to the error, right? So the lower the better. Not always, but we'll see. The other way will be that you change your model, which is not always very, very good. In our model, we say that the P was 50%. You could move your P to the 70% or to the 90%, and then this will change, right? Because now everything, if this is 0.5, now our distribution will move to here, right? And now our 14 is going to be more like here than here. So you will have much more larger. So this is one way of doing this. I would not advise to change the model, because the model is what you are relying on. If you start playing with the model until you get the result that you want, then it's not a good idea, right? And the other way to change the level of error will be to get more data, right? So the more data that you have, you remember the more data that you have, usually the more steep the distribution gets. Then our threshold also will have a less probability, right? So for example, if you collect now 40 times, if you ask 40 times for your aunt to drink the tea, even with the same model, and now instead of course 14, your threshold is 28 because you have to double the threshold too, the probability is much lower. So these are 3 ways that you can adjust the way that you will be concerned about your error. You can move the threshold, you can change the model, or you can increase the number of data. I would say that the better is to increase the number of data, the second is to change your threshold, and the third is to change your model. Now, one note here is you can see the more data you have, always the p-value or the threshold will be much smaller. So this is something that is, again, against this p-value concept. You always, if you keep collecting data, you're always going to get significant results. They're always going to be significant what you're saying. So you have to be careful with that, because with a huge n, you're always going to get some significance. And this is something to keep in mind, again, putting in context of what you're doing and looking at other parameters except the p-value as well. So, all right, so this is, so far we are okay, right? So this is for the binomial distribution, what we can get. So one difference between what we have been doing, which is estimation and testing, is in both cases we have random variable, right? And we have some distribution that we assign to this data. And what we did before was trying to find the parameters of the distribution. From an infinite set of parameters, we choose someone that fit our distribution. What we are doing now is these parameters is like the Dijon set that we are looking at the same time. In some of the parameters will fit the hypothesis, the null hypothesis, and some of the other parameters will fit the alternative hypothesis. And in our example, for example, the parameter of 0.5 will define our null hypothesis, and from 0.5 to 1 will define the alternative hypothesis. So the data that, if the data belongs to the first distribution, or the first part of the distribution, then we will go for the null hypothesis. If the data belong to the second part of the distribution, we will go for the alternative hypothesis. What I'm saying is, with our threshold, we are dividing our distribution in 2, and if the data end up here, you are in the null hypothesis. In the data end up here, you are in the alternative hypothesis. Sometimes they call it control region, the null hypothesis, the null region, and the critical region to the alternative hypothesis region. We have been saying also about our alpha level, right? It was our threshold, and that we have to always choose our power function that is less than this threshold to be on the alternative part, on the alternative hypothesis. And this alpha is usually around this border, between 0.01 and 0.1. I would say that this 0.1 is too big, and I would say that it's usually more common that you find between 0.01 and 0.05. This is what you will usually encounter. But some people accept 10% of error. For me, that's a little bit too high. Of course, 1 minus alpha will define our null hypothesis. So you can already see one important thing is that if we have our distribution and we are here, our threshold C, and let's say that we pick it such that this is 0.05, right? There is a 0.5, there is a 5% chances of making the error of rejecting the null hypothesis when you should not have rejected. But the lower you do this, you increase another error, which is the error of not rejecting something that you should have rejected, right? And this are the 2 kinds of error that we have in statistics or testing, hypothesis testing. The first error, or the error of the first kind, is the error of rejecting the null hypothesis. This is the null, and this is the alternative. Rejecting the null hypothesis when you should have actually not rejected it. And the error of the second kind, which is not rejecting the null hypothesis when you actually should have done it. And this is what you can see here in this table with the reality and the decision. So you can see that it's also a threshold, right? And this is what you will have to think about it when you do your analysis. If you, some people say, oh, yeah, I want to be very, very sure, so I go to an alpha 0.000001. Well, then probably it's going to be very hard to find any significant or you will never say that your aunt is very good at drinking cup of tea, because she has to be excellent, 20 out of 20 or 19 over 20, and then probably not happen. But also, if you set up your alpha too big, like 0.1, for example, then probably you're going to say that your aunt is really good when she's not that good. So this trade-off is what you have to play with when you're doing hypothesis testing. But like I say, a standard value that everybody accepts is this 0.05. It looks like 5% of error is good, and it feels good. So what we have been doing so far is what is called a binomial test with a single tailet. And it's a single tailet because we have been doing a threshold on the right side. If this is the middle, we have put in the threshold on the right side. And this is another example of that. I will go for a two-tailed test in another slide. But let's go for the example. Let's say that there's a new therapy that you, as an engineer, have helped to develop that you think is better than some standard therapy. I don't know. The therapy is solving, I don't know, ignorance in the world. I don't know, whatever. That would be cool, actually. And let's say that the standard therapy have a success rate of 50%, so it's very crappy, the therapy. And so then you will claim that your therapy have more than 50% chances of solving the problem, right? So again, you ignore less than 0.5, and your null hypothesis will be that it's equal to 0.5, right? So if we set up the hypothesis here again, it's pretty much like your aunt, right? So we say that our therapy will have a probability larger than 0.5. We assume this is binomial because it's success rate. And the null hypothesis will be that it's equal or less than 0.5. Equal, I would say. So again, define our function here, and our function, right, has to be less than alpha to define our critical value, because now we have our binomial distribution, but we don't know this guy here. We set up it in last time because we say 14, because I thought 70% is good. But now we have to find a C such that the probability here is equal to alpha. Okay? So the probability in the binomial case has to be equal or less than alpha. Here, one simplification is because P is equal to 0.5, right? So P to the j times 1 minus P to the n minus j will be 0.5 to the j times 0.5 to the n minus j, and then this will be just 0.5 to the n, and this is what you have here. Okay, just because because P in this case is 0.5. So now we have everything. So we have our probability has to be less than alpha, right? So any k, then we will have to find the k, this k c here, such as is the minimum that will be that our probability is the minimum value here in this axis, that the probability will be equal or less than alpha. This is what it's saying here. So we're trying to find this parameter here. And how we do that? Well, in this discrete world, we can do it actually pretty simple. Let's say again that we have 20 samples. And this is the binary distribution for P 0.5. So K will be we have to find this C, such K, the probability of K will be less than our alpha. And here our alpha, we choose it to be 0.1 for some reason. So how we do that? We go from the right to the left, right? Here, still low, 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 low. 14. 14 give us 0.057. Well, it's still not 0.1. Let's go to the next one, 13. With 13, we are already exceeding. So it will be something in between. So our threshold will be 14 again, in this case. And that's the way that you find your critical point. Anything that goes to the right of this critical point, you would say that your therapy is good. Everything that you go to the left of this critical point, you would say that your therapy is as bad as the other one. All right? Good. One thing that is important here. Every time that you reject the null hypothesis, you can say, with an alpha level of error, we can say that our data suggests that our therapy is better than the other therapy, with a 5% of error or a 10% error in this case. When you cannot reject the null hypothesis, you cannot say that your new therapy is as bad as the other one. You only can say that with the evidence that you have, there is not enough evidence to say that your therapy is as good as the other or better than the other. You cannot say anything, basically. That's all that you can say when you do hypothesis testing. All right, so that's what I was saying here before. So now we go to a two-tailed test. And the two-tailed test will be the case when you're actually having two thresholds, one to the right and one to the left. And this happens when you want to say something that is equal or different. So if it's different, it can be larger or it can be lower. And that's where the two tails come to play. So this is basically it. So our null hypothesis in this case will be that P is equal to P0, and that the alternative hypothesis is different. So it could be larger or it could be lower than P. Okay, and that's what you have to test on the two sides of the distribution now. So now you have two cases. You have the K1 that it goes from 0 to L, we call it L here, and from K to N, so we call it this K. Okay, so you have two thresholds now, and you have to find it out. So how you can do that? Now you have the union. You need to find this part of the distribution and this part of the distribution. So you need the union of these two, right? And this is what I'm seeing here, union. So now the power function is going to be split in two parts, one for the left side of the distribution, and the other to the right part of the distribution, right? So again, we can play our trick here because we still think that P is 0.5. So 0.5, we do the same thing. So now you have 2 times 0.5 to the power of n. And this has to be equal to or less than alpha, right? So since you have these 2, you have to pass these 2 here. And you will have that is actually your alpha now is divided by 2. Because between the two tails, it has to form your alpha. That will be your error, because you will have error to make it to the right and error to make it to the left. So if you say that you want to have an alpha like 0.5 here, then your alpha divided by 2 will be 0.05. So you want to have 0.5 here and 0.5 here, right? So let's find our K and our L. It's simple. You come here, And you say, no, 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 14, 15. 15 is already below that. You go here, 5 is below 0.5 alpha divided by 2. And basically, you just have to set up 1 because since it's symmetric, the other is going to be just n minus k. All right? This is also a trick. But this is how you work it out. So this will be our binomial test when you have fail or success rate and you want to see if something is better than the other or different than the other. So what you are saying is basically, are you good enough in something? Are you succeeding more than the other person? Right? This is the testing. So a little bit note on p-values. In p-value, we already saw that this is actually the probability of making this error when you have the data that you have. And this is basically what I'm saying here. And you could say, all right, you use this threshold, and you say if you are to the left or to the right, in this case, of this threshold, you are not rejecting the null hypothesis. Or you could calculate the probability of whatever you are. Let me go back to, I think there is a more clear. Yeah, here. It's already messed up by me. But you could say here, you could use C and say, if it's lower than C, reject. If it's larger, accept, right? The hypothesis. If it's to the left, reject the null hypothesis. To the right, reject the null hypothesis. Or you calculate the p-value of your data, whatever it falls, and you say, if it's below alpha, then you reject or not reject. So you could calculate the p-value and compare to your alpha. If it's below your alpha, you are good, you can reject the null hypothesis. If it's above the alpha, you cannot reject it. So that's the other way to do this. Both are the same because you're talking about the same thing. Okay, so basically this is what I'm saying here. You will calculate the probability or your alpha asterisk. In this case, is the probability of your data. And you will compare this alpha asterisk to your alpha. If it's below, reject. If it's larger, not reject. This is basically what is saying in this slide. And for the two tails, it's the same thing. So in our case, for example, 14 out of 20 is nothing that what we have calculated is 0.057. And we will say, well, this is right in the decision border, so we can reject or not. That will be your thing. So you can say, is it exactly there? Can you reject it? Well, some people say no. You still are very conservative, so you will not. Some people will say, yeah, it's fine, because it's really in the border. That's another story. All right. So I hope you have now an introduction of how you do a hypothesis testing. In the binomial case, simple one, what is a p-value? What is the critical border that you have to define? How you do it in the one side and the two side or two tails, right? So this is just the beginning of the whole story. There is a whole set of testing that we will go through this from now on, and we will use the same concept. We will use this idea of having a distribution, finding the critical borders, finding the p-values, and say if something is different to other things or something is better than the other things. There are at least three types of tests. One is to test a distribution. So if you want to see if the data fit a normal distribution or a gamma distribution or a beta distribution, there are tests for that. And to compare samples that you have collected, there are at least two type of, or the big two type of tests that are the parameter test and the non-parametric test. These are the two big worlds that in statistics exist. The parametric tests are the tests that you have a distribution, that you can fit a distribution, in particular the normal distribution. If your data fit the normal distribution, you will go for the parametric test. If your data does not belong to the normal distribution, then you will have to use other tests. And this is important because some tests are designed specifically when your data is distributed in a normal fashion. And you cannot use it for distribution in another distribution because you will be making wrong assumption because the test is not designed for that, okay? Because of the derivation of the test itself. So that basically divides this table in two. To the left, non-parametric, to the right, parametric. And this is showing in a glance some of the tests that exist. There are more than this. And the classification here is the type of data that you have. Nominal, ordinal, or interval. Nominal will be something like female and males, so something that you cannot really count, that you can say there is this and not this, but that's it. Ordinal will be something that you can, is not continuous, but it has some kind of order, like colors, for example, blue, yellow, white, whatever. And interval is what you probably will encounter more often. That is something that is measurable, like the temperature, or I don't know, the number of cars per minute, whatever. It's a value, okay? So for the nominal, for the ordinal, and for the interval classification, you have another classification, which is if the data is independent or dependent. What it means is if what you have collected now is dependent to other data that you are collecting later or before, right? For example, if you collect how well I walk when I have my eyes open, so let's say how fast you walk when you have your eyes open, and then you measure how fast I walk when my eyes closed, well, these two data will be related because are measured to the same person. So they are, no, they are not independent. Now, if I measure how you are walking and then I measure how I am walking, then these are independent because they are two different persons, just to say something. It could be other things, but this is one example how independence works. So there are different tests for independent or dependent data. There are different tests for the type of data you have, and there are different types for how they are distributed. We will go over all, I think, all these tests. Yeah. And we will explain it more in detail. So let's go for an example of a parametric test just to have an introduction to this. Parametric test, it means that it has to follow a normal distribution, so your data will be distributed in a bell shape, right? Let's say that we don't know the population, we know the population variance, right? So we have taken a sample, but we know that this sample comes from a population with some variance, okay? For some reason, we know it. And let's say that we wanted to know if our average is equal to some mu, right? So equal to some mu naught, that we call it here. So we're going to set up a hypothesis testing where we're going to say, yeah, mu is equal to this mu, the population mu is equal to the mu naught against the alternative that is different. So you can see already that is a two-tail, right? So the first thing will be to set up our alpha, right? So how much error you are okay with, right? On rejecting the null hypothesis when you should have not rejected it. The second step will be to calculate your actual average that you have from your data, and then it comes what we did before with the binomial distribution, but now with the normal distribution. What we have to do first, we have to standardize, right? Why we standardize? Because for the standardized and normal distribution, we have tables. And then it's easy to look at the critical values that we found for the binomial distribution. You can find it in the normal distribution much more easy, right? Or if not, if it's possible, let's say. So how you standardize it? You remember this. You subtract the mean, and you divide by the variance of the sample. That is the variance of the population divided by the mean the root square of the number of samples. And with that, now you will have to find your critical value, right, C. And this is where if you have your standardized it in your table, you will have values for the probability for all the C here, right? Yeah, you can imagine, not all, but most of them. You cannot write infinite number of values in a table, but you will have a lot. And then you will have to pick the one that give you your alpha. And this will be your C here, okay? Right? And then, if your value is within your value that you are testing against here, within this plus C or minus C, then you are in the null hypothesis and you cannot reject it. And you can say that they are equal, or at least you cannot say that they are different. But if your value comes outside this, in the true extreme, then you have to reject the null hypothesis, and you will have to say that your mu is different than mu naught. All right? Is that, let's say, clear? Good. The probability inside here, the probability inside the y part, the H0, is equal to 1 minus alpha, right? Because here you have alpha divided by 2, alpha divided by 2, you have alpha, so inside has to be 1 minus alpha. And this is the probability of making of your null hypothesis. So if your alpha is 0.005, your null, or here, 1 minus alpha, it will be 95%, right? So that's why this will be, so this will be the non-standardized, this is the standardized, this is what I was saying just here with all this, right? So there is one C that actually gives you the probability of alpha, or alpha over 2 in this case. It's accumulative, right? From here to there is alpha over 2, from here to the left is alpha over 2. So you have to find in the table the probability that your data is between these two borders, and remember that it's symmetric around the 0, so it's the same that 2 times the phi function minus 1, and this has to be equal to your p, right, your alpha. So then you will have to find the C such that the probability inside is whatever you put in your alpha, so 1 minus alpha divided by 2. Let me show you, it's easier to see it here in the next step. So once you have your C, the C point here in the distribution, you standardize your values that you calculated, and you see if this value is less than C or larger than minus C, then you cannot reject the null hypothesis. If it's larger than C, you reject it. If it's lower than minus C, you reject it also. That's all. So now with the example, I think it becomes a little more clear. So let's say that now we have measuring nails. So we came from measuring screws to measure nails. And these are our measurements. We have 10 measurements of nails. We know that the variance of the nails, so the length of the nails is around 9 millimeters square. Okay, the area, whatever. No, this is sorry, the variance is square, so it's length, 9 millimeters. And you want to see if your average is around 22 millimeters with this variance, okay? And you want to be sure by 1%. So your alpha will be 0.01. So you accept an error of rejecting the null hypothesis of 1% when you should not have been rejected. So now you set up your hypothesis here. The first one is that it's equal, actually, to 22, whatever you're saying. And the alternative will be that it's not equal. So you can see already that it's a two-tailed test. So what you do, first you set up your alpha, we did that, 0.01. Second, you find your critical values by standardize it, right? And now you have to go your table. How you go to the table? The probability of the nulls will be that this standardized value is between C and minus C, right? That is what we saw. Minus C, C, here is 0. So this part is rejecting, this part is rejecting, right? Null hypothesis here. So this is what I say. It has to be equal to 1 minus alpha, right? So it has to be equal to 99%. Now, it has to be equal to 99% to the both border. So it will have to be equal to 99.5%, 99.5% to the left, 99.5% to the right. So you have to look for the value in the table of 0.995, not 0.999. And that gives you a C of 2.57. So our C here is equal to 2.576 in the standardized normal distribution. That gives us an alpha divided by 2 of 0.01 divided by 2, right? This critical value. Whatever to the right is rejection. Whatever to the left or minus C, so minus 2.576, it will reject. So this is what I have here. For now, we have to calculate our data and see where our data fit in the standardized. So that's what we do here. We calculate the average. The average from this 10 value that we have measured, it gives us 20 millimeters. We standardize this value by subtracting the mean that we are actually assuming that is. And the variance divided by 2, the root square of the variance gives you the standard deviation, so it's 3 millimeters, so on. So our value is minus 2.08. This is within our C and minus C, and then we cannot reject the null hypothesis, so we cannot say that the true mean is different to 22 millimeters. All right? Is that clear? We came here in this region here. All right, good. Let's go for the second test, and I think it's the last one for today. Let's say that, and this is to see a one-tail example. Let's say that now we have collected an n equal to 10, so 10 samples, and we again know the variance, that is 4, and we know now the average also. So we don't need the even data, we have everything. Now we want you to test again if this, the true mu is less or equal to 10, or if it's larger than 10. So again, null hypothesis equal or smaller, alternative hypothesis larger than 10. And we want you to do this at an alpha level of 0.05. Okay, that's our assumption. So first step, set up the alpha, we did it. Second step, find our C, right? Now our C is going to be only here, right? Because larger than 10. So we only need a C here. So the probability of U that we have here has to be larger than C. It has to be equal to alpha. So here, alpha, right? So this is what we want to have. This is our critical value. How we do this? We just go to the table now with 0.95, right? To the left, 1 to be less than the critical value has to be 1 minus alpha. So this is 95%, this is 5%, okay? So we go to 95% to the table, and what we found is our C is 1.645. So C is equal to 1.645. Now this is our critical value, and now we have to find our mu with our data. We already saw, or we have it, that average is 12, so 12 minus our assumption that is less than 10, right? Divided by the standard deviation, divided by root square of 10. It gives us sorry, here, it gives us 3.162. 3.162 is larger than 1.645, then we can reject the null hypothesis at the error of 0.05. All right, that's simple. The other way would be that you actually calculate the probability of having this value. So you could go with this value to the standard table, look at the value of the probability, and this will be your p-value. If this p-value is smaller than your alpha, in this case 0.05, then you reject again the null hypothesis. I'm pretty sure that the standard normal distribution, well, I'm sure, because if not, it would not be true, is less than 0.05. I don't know the exact number because I don't have the table. All right, so with this, I think we finish. Just you probably know PhD comic or not. If not, you should look at it. It's an old page, but really cool page. So how we actually look at this. So whatever below 0.5 is actually good usually. Highly significant if you are more. Some significant here. Well, here you already, if you are really in the 0.5, you want to check if you really did it well. Then here's when you start to say, I wish it would be less than 0.5. Then here it's like, yeah, it's a suggestion. And then, oh, yeah, that's really good. Yeah, so it's fun, but it's actually true. Usually you're like, wish it would be significant. If you want to be significant, sometimes you don't want to be significant. All right, with that, I think, I hope you have a grasp, hypothesis testing, how it came from. We will increase complexity now, how the tests work. This is just the basic, but everything will kind of based on this concept of the critical value, the p-value, your confidence, and type of error 1 and type of error 2. All right? Good. With that, thank you, and I'll see you next week.